Welcome to today's deep dive into one of the most enigmatic and captivating topics in modern science: antimatter. We're going to explore what antimatter is, its historical context, how it's produced, its applications, and its profound implications for understanding the universe. Get ready for an exciting journey into the universe's most mysterious substance. Let's start with the basics. What is antimatter? Antimatter consists of particles that are mirror images of the particles making up regular matter. For every type of matter particle, there's a corresponding antiparticle. For example, the electron, a fundamental particle of matter, has an antiparticle called the positron. While electrons have a negative charge, positrons have a positive charge. This opposite charge means that when electrons and positrons meet, they annihilate each other, converting their mass into energy in the form of gamma rays. This process of annihilation is incredibly efficient. According to Einstein's equation E equals mc squared, the energy released when matter and antimatter annihilate can be millions of times more potent than chemical reactions. The concept of antimatter has a rich history that began with the theoretical predictions of Paul Dirac in 1928. Dirac's work in quantum mechanics and relativity led him to propose the existence of antiparticles, which were confirmed by Carl Anderson's discovery of the positron in 1932. Dirac's equations predicted the positron, the antiparticle of the electron, which was a groundbreaking discovery. Anderson's experiment involved cosmic rays, and his findings validated Dirac's theories, earning him the Nobel Prize in Physics in 1936. Following this, other antiparticles were discovered, including the antiproton and antineutron. The development of particle accelerators, like those at CERN, has allowed scientists to study these antiparticles in detail, furthering our understanding of antimatter. Producing antimatter is a complex and expensive process. The most common method involves particle accelerators. These machines accelerate particles to near-light speeds and then smash them together. These high-energy collisions can produce antiparticles. For instance, the Large Hadron Collider at CERN is capable of producing antiprotons and positrons. In these collisions, particles and antiparticles are created in a highly energetic environment, and scientists capture these antiparticles for study. In addition to accelerators, antimatter can also be produced in certain types of radioactive decay. For example, during beta-plus decay, a proton in an unstable nucleus can convert into a neutron, releasing a positron and a neutrino. However, the production of antimatter is highly inefficient. Creating just a few nanograms of antimatter can cost billions of dollars. Researchers are continually working on improving the efficiency of production and storage methods. Despite its challenges, antimatter has some intriguing applications. One of the most notable is in positron emission tomography, or PET scans. In PET scans, positrons are used to create images of the body. Here's how it works. A radioactive substance that emits positrons is introduced into the body. When these positrons encounter electrons, they annihilate, producing gamma rays. These rays are detected by the PET scanner, creating detailed images of metabolic processes in the body. PET scans are invaluable for diagnosing diseases, including cancers, and assessing brain function. Looking into the future, antimatter holds potential for advanced energy production and propulsion technology. Theoretically, antimatter could be used in high-efficiency energy sources or even spacecraft propulsion systems. For instance, a spacecraft powered by antimatter could achieve speeds close to the speed of light, making interstellar travel feasible. Despite its fascinating properties, antimatter poses significant challenges. One of the biggest issues is storage. Since antimatter annihilates upon contact with matter, it must be stored in vacuum chambers or magnetic traps that prevent it from coming into contact with ordinary matter. Current storage techniques are complex and expensive. Magnetic traps use strong magnetic fields to keep antiparticles suspended, while vacuum chambers prevent the antimatter from interacting with any residual matter. Additionally, the production of antimatter is incredibly costly. The current methods are not only expensive, but also produce only tiny amounts of antimatter. Researchers are exploring new ways to make production more efficient and affordable, but it remains a significant hurdle. Antimatter also plays a crucial role in our understanding of the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. However, our observable universe is dominated by matter, leading to a major question in cosmology. Why is there such an imbalance? This discrepancy is known as the matter-antimatter asymmetry problem. Scientists are investigating various theories to explain why matter is so predominant. Some hypotheses suggest that tiny differences in the behavior of matter and antimatter could have led to the dominance of matter. Understanding antimatter and its interactions could provide valuable insights into the early universe and the fundamental forces that govern it. Ongoing research into cosmic rays and particle physics may eventually reveal answers to these profound questions. Looking ahead, the future of antimatter research is filled with exciting possibilities. As technology advances, we may see significant breakthroughs in antimatter production, storage, and application. Researchers are exploring new materials and methods to improve the efficiency of antimatter production. Advances in magnetic confinement and vacuum technologies could make it easier to store and manipulate antimatter. If these challenges are overcome, antimatter could become a cornerstone of future energy systems and space exploration. Moreover, ongoing studies in fundamental physics may uncover new insights into antimatter and its role in the universe. As we continue to explore this mysterious substance, we may uncover even more about the nature of reality itself. And there you have it, an in-depth exploration of antimatter from its fundamental properties and historical discoveries to its current applications and cosmic significance. Antimatter is truly one of the most fascinating substances in the universe, with the potential to revolutionize our understanding of physics and our technological capabilities. If you enjoyed this deep dive into antimatter, be sure to give us a thumbs up, subscribe to the channel, and hit the notification bell to stay updated on our latest content. Share your thoughts and questions in the comments below. We'd love to hear from you. Thanks for joining us on this journey into the heart of antimatter. Until next time, keep exploring the wonders of science.